Okay, so hello everyone, welcome to section 12. And today the topic would be 4-point rotational springs or 4-node rotational springs. And this is the new element we introduced last time when talking about using bar and hinge models to simulate the behavior of a mural origami pattern. Right, so last time we say that to capture the folding between these inside an origami in the creases, we will need to use this 4-node rotational spring that use 4-node IJKL with the IJK defining one panel and the JKL defining another panel, and it captures the folding in between. So this time we're actually going to be looking to the theory behind these springs and try to derive them again using the central difference method. So before we start, let's actually do a little bit of review of the 3-node or 3-point rotational spring we derived in section 10 just 2 sections ago, right? So we say that with in a planar structure, we can actually capture that rotation between these two lines using 3-node. And when we construct that total potential, we're going to be using a total potential in this form. So U spring is basically 1/2 K times the difference between your current angle and the stress-free angle, and then take the square of it, right? So that's the potential we used to derive this 3-point rotational spring. So in the 4-point system, the exact same formulation still applies, but the only thing we need to change is that in the 3-node spring, the theta is a function of xi, xj, and xk. So 3-node. Whereas in the 4-node spring, the theta is now, we have one more node, right? So instead of ijk, we have I, xj, xk, and then xijkl. There's this fourth node that we need to add into the representation. So with the 4 nodal coordinates, the way we solve the angle is actually quite straightforward. So let me actually draw these plots to demonstrate how the calculation works. So this is I, J, K, and L. From the panel IJK, we can find the normal vector. It's going to have M1 there. And then from JKL, we can find another normal vector, N2. And then we find the angle in between M1 and N2. That's how we figure out the angle in between these normal vectors. So with the angles, we are now able to solve for just basically create a potential, right? Using these equation we've been using for the 3-node rotational spring. So finding the normals are not hard. So for instance, in this function, so this first function we created in this file is just to find that theta angle using the 4-node. So for the first normal, what we are doing is basically we find two vectors. Vector 1 is from xj to xi, so that's vector 1. And then the vector 2 there would be um, from j to k, right? So these are the two vectors. So after we find these two vectors, we normalize them to have unit 1 length, and then we take a cross product that will directly bring us the normal, right? The cross product gives us the normal. And then the second case would be just using, again, just replacing xi with xl. Then this would be our vector 1, that's xl minus xj. And then xk minus xj would be the vector 2 for the normal 2. And these two vectors, if you cross them, first normalize them and then you cross them, you get the normal 2. And after that, we just use the arc cosine function to find the angle associated with these two normal vectors, right? So that's exactly what we've been doing. Let me put it side by side. We did the same thing in the section 10 when we are finding the 3-point rotational spring, the same arc cosine function, dot product of the two vectors divided by the norm of the two vectors, right? That's something we've been doing and we should be very familiar, probably even since high school, I don't know. But anyway, now that we have this, let's try to briefly verify it, and this set of the code is just to verify that. We created this four node. It's gonna give us an angle of about 90 degrees. So let me actually draw these four node for you. So we're gonna be looking at a XYZ coordinate. So the first node is 1, 0, 0. That's here along the x-axis, I. The second node is 0, -1, 0. So -1 means negative in the negative y-axis. The third node, the k node, ij, the kth node is 0, 1, 0. So it's here, k node. And then the L node would be 0, 0, 1. So that's going to be above the z-axis. So if we draw the two panels, it would be on the top, there's one panel, right? And then on the bottom, there's another panel, and apparently this should give us a right angle. And indeed, we find 1.57 rad or radius. That's 90 degrees, so pi over 2 is exactly 90 degree. We typically use radius unit in the code because that's quite convenient. And after that, with the theta angles found with the function that can allows us to reliably calculate the theta, we can create this potential, right? Using the exact same equation, except that this time when we calculate the angle, it's 4 node. All right. So after that, we just apply the central difference, right? That's what we've been doing when deriving the bar and when deriving the 3-point rotational springs. It works pretty well, and there's no reason why it doesn't work. It does not work here, right? It should work. So let's take a look at what we're going to be doing and maybe do a little bit of review of by comparing what we will be doing for the 4-node rotational spring with the section 5, which is the central difference in the bar element. So let's compare the equations here. So on the left is the bar element. On the right is the 4-node rotational spring. We have 4-node. So our force vector, the Jacobian of the potential, it's a little bit longer. It has now 12 by 1 dimension. But it's still the same thing, right? When you look at the all of these elements inside this vector, the first three would be forces on node I in the XYZ direction. The second three, it's dot 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 here, but you can imagine they're there. It's gonna be for the jth node, XYZ direction, directional forces, and then the third three um, um, elements there would be for the kth node in XYZ, and then the final three is listed here, the L node XYZ, right? The component for the forces. So when we are solving for each of these components, we're going to be using these exact same central difference approximation. So there's really no difference if you compare the central difference for, let's say, the xi direction, right? It's just that we now change the potential. The potential in the bars only have 6 input variables, so the location, the nodal coordinate, the I in the ith node XYZ and also in the jth node XYZ, but this time I have the additional kth node and also the lth node. That's it. But still, you move along the xi with the small step delta in a positive direction. You move in the backward direction, negative delta. You find the two potential, you subtract them, and you divide that difference by 2 delta, and that gives us the approximation of these directional force along the xi direction. All right, so quite straightforward. And if you compare the functions we created to do this calculation for us, you're just convinced more, right? They are the same thing. So this time the calculation function for the four node rotational spring, it really is just like copy pasting whatever we have for the bar to the spring and then add two node. That's it. So the potential, of course, we're not using the potential of the bar, we're using the potential of the four node spring, but we take a step in the forward direction, one step in the backward direction, find the difference. So that's the difference in the potential. There's a minus there divided by 2, divided by delta, and then that's the force. That's the force in that direction. So in addition to the ith and the jth node, there's just two more there because we're now having four nodes, so kth and lth node. So this four do basically just loop through the x, y, and z direction. So everything feels the same, right? So if we further compare that with the three node spring, in the section 10, it's also the same here, right? So this one just has this case note. So just try to compare that functions and then convince yourself that the the approaches is actually the approach we're doing here is widely applicable regardless of the number of nodes you're using to represent the potential. All right. So in the next section, what I would like to do is to really just visualize these force from the springs, from the three node rotational spring and also the four node rotational spring. So on the left, I have section 10. This is three node rotational spring. Remember, we did two sections ago, right? When we move the springs, depending on the relationship, it will give us plot this force depending on how well the theta matches the theta naught. So let's run it. So in order to run that, I do need to add a element and solver into path. Okay. All right, that will allow us to run this code. Let me run it. All right, so basically, if you have the theta angle to be the same as the theta naught, you don't have any forces, right? This is the three node rotational springs. And on the right, it's a four node rotational spring, and we're going to be doing the same thing. Let's hide the code, and when the forces, the theta naught is the same as the theta, the current angle is exactly the rest angle. There's no forces going to be generated. But when we fold it to a angle that's different from the stress-free angle, we start developing forces because remember, this is basically paper clips. You want to go back to the rest position where there's no strain, and it prefers that. The natural prefers a low energy state, and when your theta matches theta naught, the potential is zero, and that's what nature likes. So the same thing here, if you do these to the 3 point, when they're different, force is going to be generated. It's going to try to push theta to theta naught. So this matches our expectations. So the only difference between the left and right is that this is three node, it's a planar angle. This is four node, it's basically the angle in between two plane, but everything is mostly the same, right? So after that, if we keep going into the Hessian calculation, we will find that stiffness matrix of this four node spring. So we're just going to have this additional dimension here. So remember in the section 10, we start doing these group block notation. So each of these submatrix is going to be 3 by 3. So we have a full 12 by 12 Hessian matrix for these four node spring on the right. And each of these component is a 3 by 3. Just pay attention here that these xi and xj, they are bolded. So it means that this is taking the derivatives about the vector. And that will give us a 3 by 3. So each of these highlighted notation is actually a 3 by 3 matrix itself. And for instance, this one is written here. That's the 3 by 3 submatrix. And here in this second equation, you can see that this xi and xj, they're not bolded. So, and then you start seeing yj and then zj. So this is actually the scalar variable. All right. So, but still, the operation we're going to be using, the procedure we're going to be using is we're going to take out every column from the stiffness matrix, and we're going to say that for each of these columns, there's going to be a shared operation. So there's going to be a shared derivative about one axis. It's either xi, yi, zi, doesn't matter, but there's going to be a shared axis. And because of the way these matrices are defined, and if we take that shared derivatives out, the rest will be just the force vector we just calculated. So it basically simplifies into this nabla x U spring, which is exactly the force calculation. So this is also the same for the bars that we did a while ago in section 5. So with that knowledge, what we can do is actually apply a single step of central difference to the force vector that we found, and that will give us a way to approximate the entire column in the stiffness matrix, and that's exactly what we did. So if you go into these local stiffness calculation so basically the single four-node rotational spring, you can see that the structure of this calculation is just identical to that force calculation. We've seen these, right? So the only difference here is that here the K, the output is 12 by 12. It's a matrix, not a vector. And each time when we are doing this calculation, we are calling this local spring force function rather than the potential, right? So when we're solving for the forces, we're calling the potential when we do the central difference approximation. But here we're just doing we replace that with the local force. And here we use this notation to basically throw the entire result. It's going to be a column vector and paste that in the right location in the K matrix. So that's what we do. So this process is actually similar to the section 5 and section 10. Sorry for the typo. Let's just fix that while we are talking about it. But anyway, with that, the final thing we want to do is to actually check the results that we just coded, right? We now coded a function that can give us the local stiffness of a spring and also a function that can give us the local stiffness of the local forces of the four-node spring and also the local stiffness of the four-node springs for a single spring. And the thing we're going to be doing here is to compare that with our stock solution. So we're going to create the CD central difference element rotational spring for node. That's the one that we use in section 11. Well, actually, I think we used the vectorized version, but if you change this vectorized version to CD, you can still run it. So the package actually supports you to do that. But anyway, so let's compare because we're using central difference to derive it, so let's actually compare that with the central difference element in the package, so the stock element. So we're gonna make the delta to be this value, and we're gonna try to compare the result, and let me run it. And then as you can see, when regardless of this, let me hide the code, regardless of these different thetas, the stock force and the forces found with this code, they matches each other pretty well, right? So everything looks pretty nice, and also the stiffness also matches fairly okay. So yeah, they are identical. That's exactly what we want, right? So therefore, we are pretty happy about it. And we can also change the step there, and you can see that this also the result is the same. So the delta step do changes some of the results, but still the stock function give us the same result as what we've just coded. So that's nice, right? And the one more thing I do hope to just briefly mention, and actually go back to here, is that if you stare at the stiffness matrix, you can see that as we change the delta, the value you start seeing some of the difference there because of the digit, right? The digit actually starts moving around. And if you use a too small of a value in your delta, you might actually run into a bad result that's not so realistic. And this is because of the numerical errors that we found when using the central difference. So at the end of the day, central difference is just approximating that stiffness. So if your step length is not selected to be a good one, you might run into numerical issues. So basically, in any sort of a programming or any sort of machines, like a virtual computer programs, the numbers are not the real numbers we use in math. So in the computer, we have these, floating point number that we're actually using, and it's not continuous strictly. So because of that, and also the machine epsilon, so basically it's typically in the orders of 10 to the power of negative 17th, if we are talking about, say, double precision floating point number. So it's machine epsilon, this epsilon. 10 to the negative 17, around that value. So what it means is that if in the computer, if you do one add epsilon, it will actually gives you one back. And this will actually makes you to start losing some of your accuracy if your delta step is too small. The difference is too small, so that I start losing some of the accuracy in my computation. So this is purely numerical, and therefore, when people are using some of these numerical ways of finding, say, the gradient, we need to be cautious, because if we don't select the delta right, we might run into issues. So typically, just play around with it until you see a result that's reasonable. Or you can actually do a little bit of a small calculation. You can find the potential, and then you move your deformation, find another potential, see that if the two potentials are identical, then probably your step is too small. So that's some of the things. Hope that don't didn't blow your mind out, but depending on your background, this might be your first time hearing the term machine epsilon. But because we're dealing with the coding and this is all inside a computer, I do feel that you do need to at least get some ideas about what's going on in the computer. So if you want to learn more, just Google floating point number, and I believe Wikipedia can give you much more information on that. All right. So before I close out, I actually want to add some comment here about the central difference procedure, and more specifically, I want to discuss the drawbacks. So it's a method, right? Just like any simulation, any model, any method, there is pros, there's cons. So we've been bragging about these methods for a while, and I do hope to take a step back this time and actually start talking about what are the drawbacks. So one of the biggest thing that we aren't able to capture well with the central difference here is that the system needs to be elastic. So We can do hyperelastic, we can do nonlinear material responses, no problem, but we need elastic. So because it's based on, taking derivatives of a total potential. So if the system has a potential, it's conservative, and there's no energy lost. But if you have a viscous response, or if you have a plastic response, both of those material models, elastic and viscous, they usually are correlated with energy lost, so dissipated energy. When that's also in the system, you cannot just directly use these central difference. You can probably still use the central difference to capture that elastic portion, but you definitely need to add in more in order to take into the consideration of the viscosity and also the plasticity in the material response. So those are not directly supported with these procedure I outlined here. And in order to, let's say, integrate some sort of a simple plastic model, such as for instance, homogeneous strain hardening, plastic behaviors, we do need to do something else. And more specifically, we actually need to solve for the analytical solution and to separate the material response part from the rest of the part that's taking care of the large geometric deformation. So the package actually already supports you to do that. There is a bar elements that support the plastic homogeneous strand hardening behavior, and I will try to make that example uploaded as soon as possible. But then for the theory part, I'm still thinking about how to teach that material. It's coming, but then it's not yet there at this moment. Uh, I'm gonna make you a promise that it's gonna be added when I have time. But anyway, some final more comments about the references and also related classes. So if you want to learn about especially the analytical way of deriving a model like these, go to read that Leo and Paulino paper published in the Royal Society Proceeding Ace. This is definitely a fantastic paper. So if you go into their appendixes, you will find how we typically, block create this block representation of matrix and solve it in a 3 by 3 block. So these are the solutions there. And also it gives you an idea, the derivation also gives you an idea how we actually separate the part into, multiple components, like material responses and also the nonlinear geometric, the stiffness part. We try to separate them into different components so that we can attack problems like these material responses more viscosity and also plasticity more easier. All right, so that's the kind of the final comment regarding the reference. And for related classes, it's going to be similar to section 5, so I don't think I want to spend more time, basically just relist all of these again. And with that, I really want to thank you very much for your attention. And as always, I would like to wish everyone have a great rest of your day.